upload the recording by today. All right. So you will get the recording. Don't worry. And if you still didn't get the recording till 10 p.m., then text me. Like I'll upload the recording. Okay. Okay. Any doubt on the transistor or
Sir, can you provide a little brief about alpha and beta, how they came?
y- yes. Fine, fine. So uh, like if you recall from the last class, we define our beta like current gain. It's the ratio of current from the collector upon current from the base, right? So actually, if you recall from the last session, you know that most of the electron from the this emitter part, it will move towards the base part, right? And I also mentioned that many of the electron will get attracted towards the collector side because here you are applying more potential and very few number of electron will move to this side, right? So the flow of electron will constitute to the current, right? And this equation, and if we want to represent this mathematically, we represent a current gain. So imagine your current gain, let's say the value of beta is, imagine it's 100. So what does this tell you? It tells you, let's suppose if hundreds of electron, if they will pass through this collector side, then only one electron will move to this base side, right? Because IC will be equals to 100 times of IB. And you also know that current is nothing but a delta Q upon delta T. So I can also write it like this. Delta QC is equals to 100 times of delta Q T, and here you will have delta T, and here you will also have delta T. But since both terms are same, we are looking for the same time frame. So delta QC will be equals to 100 times of delta QB, right? And this is
Yes,
the
sir.
like, yeah, this is why we like to represent this using the current gain. It just tells us like for how many flow of electron through the collector, there will be a one electron which will move through the base side, right? So this is just a current gain. And there you also mentioned about alpha, right? So if you recall, IC is equals to alpha times of IE, right? Current from the collector is equals to alpha times of current through the emitter. So this represent, and I also mentioned that if you're in transistor, you prefer your alpha very close to one. So this tells you that like uh, the relationship between the current from the collector and the current which is going in from the emitter part. All right. So this is not nothing but like if you like, it's just a alpha is just a number which you use to compare the like transistor, like uh how effective is your transistor. If you want like, see, you agree with me, right? If alpha is very close to one, this IC will be very near to IE, because IE is equals to IC plus IB. And since if your alpha is very close to one, if it's very close to one, just look at this term. This beta will be very close to zero if your alpha is very close to 1, right? In practical sense, beta can never be equals to 0 or alpha can never be equals to 1. But we're just looking it in the terms of limits. All right. So this is a short story about alpha and beta. Yeah.
Okay, sir.
Yeah.
Yes, sir.
Yeah. Any other doubt? Okay. So guys, Today we will discuss about the relationship between the input voltage and the output voltage. Now, what is this input and output voltage? So guys, if you remember from the last class, I call the potential which you apply on the base side as input voltage, right? Because changing this voltage leads to the motion of current through your circuit, right? And this potential at the collector side, I call it as output potential, right? Because uh, if you like, if you see the working of like, let's say here you have a microphone, and here you have wires. Let's say this is your relation of current versus time, and this is your graph. So what does this amplifier do? Let's say here is your amplifier, and it is connected to your speaker. So what does this amplifier will do? It will like take the current input and it will just amplify it. Like the amplitude will get increased, but the graph will remain same. All right. So it has nothing but it has just amplified the current and it has like outputted it to the speaker. So in the similar way, changing the input voltage will lead to the change in the output voltage. And today we will have a discussion in the mathematical term, like what is that relation? Okay. So before like discussing this, let us draw the circuit diagram of transistor first. This is your upper is your collector side. This is your emitter and middle one is base. All right. So guys, what will happen if we apply a potential less than 0.7 volt on this side? The current will not flow, right? See, if you apply a potential less than zero point 0.7, it will not, the electron will not be able to jump from this side to the base side, right? That's why you will not have any
Yes, sir.
current if your, yeah, if your potential is less than zero point 0.7. All right. So now let's have some value for our voltage and for our resistor. Let's assume I'm using a battery of let's say 3 volt. All right. And let's have a value for our resistor. Let let it be 1 kilo ohm. All right. And let's say, look at this figure, and let's say this is your first case. What will happen if your IB will be equal to 0, or V input is less than zero point 0.7? This is your V input. So what will happen in the first case? If your IB is 0, it means current through the uh, base, or if your potential is less than zero point 0.7, what will happen?
Cut off.
Yes, it's called cutoff state, because beta is equal to IC upon IB. Actually, this is not the correct way to write here in the denominator, because, but let's assume IB is very near to 0. Then IC will also be equal to 0, right? So it means you will not have any current through the circuit, and we call it as cutoff state. So in the further discussion, we will use this concept to build our switch. But right now, our task is to find some relationship between this current, this IB current and IC, and also between input voltage and output voltage. Now, guys, Let's increase, like let's start to increase our current. Let's say the current through the base. Let's give it one value. Let's say 10 microampere. And let our beta be equals to 100. So what will be the value of IC in this case? Anyone?
1000 microampere.
Yes. So the value of IC will be equals to 1000 microampere, right? And I can also write it as 1 milli or 1 milliampere, right? Because microampere means 10 to the power minus 6, and you are multiplying it with 1000. So 10 to the power minus 3 ampere, which is 1 milliampere, right? So can anyone tell me the potential at this point? At this point, let's say you are applying a 3 volt over here. The IC is 1 milliampere. What will be the potential at this point? Come on, Ohm's law.
1 volt.
Yes,
1
it will
volt.
be 1 volt. Yes,
1
because
volt.
let's, yeah, 1 volt. The answer will be 1 volt. Why? Let's look.
Sir, can you please repeat the question again?
Yes, yes. I'll repeat the question. So I was saying, uh, first case is clear to you, right? If there is no current flowing through this wire, there will be no current in the circuit, right? And we call it as cutoff state. Clear? First case was clear to you, right?
Yes.
Yes, sir.
Yes. Yeah. So so now I am saying, if let's give some value to the current flowing through this space, and I call it as, let's say, 10 microampere. So you have this relation, right? Beta equals to IC upon IB. And I have also given you the value of beta. So you can calculate the value of IC, which is equals to beta times of IB, right? Now, 10 microampere multiplied by 100, you will get 1000 microampere, right? Which will be equals to 1 milliampere. Clear? Now my question was, if if the current through your collector, if it is 1 milliampere, then what will be the potential at this point? There will be some potential drop due to this resistor, right? Because the resistor will use some of the energy from the electron to maybe some purpose, like to maybe heat itself, to give light. We don't know. We are just using a resistor of 1 kilo ohm. So there will be a drop of two potential 2 volt. Let's calculate how. So V across the resistor will be equals to IC into R, which will be equals to 1 milliampere into 1 kilo ohm. So VR will be equals to 1 volt. Clear? So there will be a drop of 1 volt potential across this. All right. And at this point, you will have potential of 2 volt. Why so? Because 1 volt is used by a resistor, right? And if you subtract, you have 3 volt, 1 volt is used by a resistor, so remaining will be 2 volt. And you can also see the difference between potential is 1 volt. So 1 volt divided by 1 milliampere is 1000 ohm, right? Clear? Is this clear till this
Yes,
point?
sir, done.
Done? True? Okay.
Yes.
Now, my friend, let's increase the current of this IB. Initially it was 10 microampere, right? Now my intention is to increase this current to 20 microamperes, and beta, still we are using beta as 100. So what will be the value of IC and what will be the potential drop or the potential at green point? Don't calculate and tell me the value of this. It will be 2 milliampere. And can someone just quickly calculate the value of or potential at this green point?
Oh, sorry, can you repeat again?
Yes, I'll repeat.
One.
So yes, it will be one. I'll repeat the question again. So
1 volt. 1 volt.
yeah, now in this case, in this slide, we have increased our current through the base to 20 microamperes. Initially, you got this case, right? Initially, when it was 10 microampere and beta was 100, you calculate
Yeah.
IC and potential
Mhm.
across this, and then you calculate the potential uh, at this green point, all right, which
Yeah.
was 3
Mhm.
minus the potential used by this. Now, now I mentioned that if you increase the current, what will be the potential at this point?
Oh, okay, got
Wi-
it. Got your
Yeah,
question.
yeah,
Yeah.
yeah. And someone calculated it, and it's one volt, right? I'll also show you how. So again, V across the resistor will be equals to IC into R, which will be equals to 2 milliampere multiplied by 1 kilo ohm. I'm just like not representing the units over here, but milli into kilo is one. Okay, yeah, just like so. This will be 2 volt. Okay, so now in this case, your resistor it's using 2 volt of energy. So if you subtract two from the initial, you have three. So only one volt will be there right now. So the potential at green point in this case will be 1 volt. Clear? Okay, now third and very important case. Now let's take a value of IB equals to 30 microamperes and again beta equals to 100. Now calculate the value of IC and the potential at green point. This is a very important case, right? Can someone just quickly calculate the
3
value of
milliampere and 3 volts.
it will be 3 volts or will it be
Zero.
0?
Zero.
If it, yeah, it will be 0, right? See, initially you were getting only initially you got 2 volt at this point. Then you got 1 volt. Now it will be 0, right? Clear? Or can I explain again? Clear, right?
Yes.
Yes. Now, my friend, this is very important. All right. So just pay little more attention. So since I'm using the current as 30 microampere and I'm getting the potential at green point equals to 0. So what will happen if I increase the IB? If I increase the IB from 0.30 onwards, let's say if I take IB equals to 40 or maybe 31 or 32, what will happen? Will the value of IC will change? Will the potential at this point will change? What will happen? You got the question, right?
Sir,
Everything
there
is
is one
clear.
doubt.
Yes. Please.
Sir, we got IC is equal to 3 milliamperes, and to calculate V is equal to IR, I is 3, and R value
Yes.
is 1 kilo ohm. So we should
Yes.
get 3 volts. No? How it comes
Yeah.
0?
It's 0. Okay. See, you are correct. The but the value which you are calculating V equals to IR, it's the potential used by your resistor. So 1 kilo ohm multiplied by 3 milliamperes gives you 3 volt, right? But what does it tells you? It tells you your resistor now has used the 3 volt of energy. And if you subtract 3 from 3,
Yes.
you will get 0 over here. All right?
Oh, okay, sir.
Yeah. See, think in another. Let's say if you have a 0 value over here. So what will be the potential difference between this point and this point? It will be 3 volt. All right? And 3 volt divided by resistor value 1 kilo ohm, which is nothing but I equals to V by R. You will get I equals to 3 milliamperes. Clear?
Yes.
Yes. So you understand, right? Why it's 0 at this green point in the third case
Yes,
when
sir.
we,
Yes.
yeah, good. So guys, now this is a very important point I want to discuss with you. Let's draw a quick table, and this is a very important table. This is IB, this is IC, and this is potential at green point. 1, 2, 3. At the first, in the first case, you use 10, and all the units in the and the unit for the current through the base is always in the microampere, alright? So generally it's in microampere, and in the IC it's yearly in milliampere. In our case, we are using it, and we will be in V. So 10, and IC was in this case it was 1, right? 1 milliampere, and potential at the green point was 2 volt. When you increase the IB to 20, your current in the collector also increase, and it increased to 2 milliampere, but the potential at the green point it drops to 1. But in the third and important case, when your current through the base was 30, the current through the collector was 3 milliampere. It was maximum, and the potential at the point green was 0. So guys, can you increase this current further? Yes, you can increase, but will the value of IC and IC will increase? It will not increase. Why? Because you can't have potential in the negative, right? So this is your maximum current you can have in your circuit. This is your minimum voltage you can have in your circuit. Can I explain again, or is this clear? Come on,
Clear, sir.
I need your interaction in this case. Clear for all?
Yes, sir.
Yes, sir.
So now, guys, we have reached.
Why will this
we-
IC stay constant after this point?
Okay, I'll explain. So let's imagine you have applied a 40 microamperes over here, right? Right. So
Yeah.
theoretically, what value of IC you should get here? It should be 4 milliampere, right?
Yeah.
Yeah. Okay. Now, since V is equals to IR, if you multiply 4 milliamperes with 1 kilo ohm, you should get 4 volt. But my friend, is it possible to have a potential of 4 volt at this point? Can the difference between the difference between 3 volt and 4 volt will be negative, right? So what you are saying, you are having a 4 volt of potential over here, and still your current is flowing from 3 volt to 4 volt. So is it practically possible? Will your in any case, will your current will ever flow from low potential to high potential? No.
No.
Yeah, so that's why we can't, even if you can increase the current through the IB, but there will be no increment in the IC, and VC will also stay constant, 0, 0, 0 throughout. Clear?
Yes.
Yes. Now, guys,
How is that excess current affecting or getting lost?
this excess current. Okay.
Yeah. Like the
Yeah.
excess 10 microampere, if I'm giving after 30 microamps, then where is it going, that part? Yeah, or
Yeah.
is it is just adjusting that IE?
Yeah. So, if according to this equation, I equals to IC plus IB, it should adjust the IE. Got it? See, since your IC can't increase further, So this whole current, the extra current which you are using, should go in the IB, right?
Yeah.
IE, sorry. Because if you even see this analogy, this notation, this analogy is also very important. See, if you give extra current, extra, like if you increase the pipe over here, what is the purpose of this pipe, of this small pipe? To rotate this blockage, right? To remove the blockage over here, to make the water flow. Even if you keep adding the extra pipe length over here, the more water current will flow through the base part, which is nothing but a current through this emitter side. All right. But in practical, in purpose, we connect our resistor at this point. Okay. So that's why we don't care about or we don't discuss about this extra current, like, because since you have like reached to the minimum voltage of your output, or at the voltage at the green point, since you can't drop this voltage further, so we generally don't discuss the like the state after this point. So we call this point at saturation point. Okay. So this is, we have reached the saturation part. Please excuse me for my handwriting. Right. So we have reached for the saturation part. So guys, we discuss about two things. First, cutoff state, and second is saturated state. Clear? So if we want to see this in the comparison basis, or on the comparison basis, we can say the current through the IB should be between, let's remove this zero here, should be in between 0 to 30 microampere. All right. In this part, your current will increase from, or will belong to 0 to 3, and V at green point will vary from uh, 3 volt to 0 volt. And now, and you will argue with me, why 3 volt maximum? Because let's say you don't have any current through this. Let's say IC, let's imagine IC equals to 0. So potential at this point will be equals to potential at this point, because there will be no potential drop. So potential at all point will be 3 volt. All right. So that's why you can have a maximum potential of 3 volt and minimum of 0. Clear? So one can say, okay, this transistor will only act like an amplifier if you use base current from 0 to 30 microampere. All right. Or it will have a property of amplifying if you use your current in this range, and you can appreciate this range is very small. 30 microampere is such a small current, but because of this you can control the current through your circuit. See, you are just varying your current from 0 to 30 microampere, but still you are able to, this microampere current is able to adjust the current in the milliampere. All right. So that's why we generally say this transistor, it also behaves like a amplifier. Like this example, whenever you speak in the mic, because of the difference in the air pressure, there is a fluctuation in the current with respect to time. And but that fluctuation is so small, if you directly connect this wire to the speaker, you will hear nothing. But if you connect this to amplifier, this amplifier will increase the amplitude of this current wave without changing its shape. And because of this, you can hear sound whenever you speak in microphone. So right now we have just discussed the property of amplifier, like transistor as an amplifier. Now let's have a look in the relationship between V input and V output. So now we are going to discuss like we have one relation, right? The relationship between the IC and IB. Like IC, the current through the collector is beta times of IB. But what is the relationship between VI and VO? Let's find it out. So guys, you uh, uh, till this point you should all agree with this equation, right? Now let's say IC1 is equals to beta times of IB1.
Sir, I have a doubt.
Yes, ask. Please ask.
So when IB and IC is 0, that time the region is cut off, right?
The what? The region.
When yes, sir. Like that state is called cut off state. When IB and IC is
Yes,
0.
yes, yes. Yes, yes.
And sir, one more thing, when IB, like when IC is maxed out, like it stop increasing, that point is called saturation.
Yes, yes. Then hello. Am I audible?
Yes, sir.
Yes,
You
sir,
are
you are.
audible.
Yes, I think can you guys hear him? I think he had just muted himself. Or was this your all out? Like you just want to know the cutoff or saturation part. Okay, so I'll continue the discussion. So I can write this equation as like IC1 equals to beta times of IB1, right? Because your like the value of IB, it can take from 0 to 30 microampere. So I can write this equation. IB will always be in between this value, okay, for now, like for our this example. Okay, now guys, I can also write it like this. IC2 is equals to beta times of IB2. Can I write this? See, I'm just using different variable. This IB, it will be anything like 10 microampere or IB2 will be 20 microampere, whatever. Can I write like this? Come on.
Yes, sir.
Yes. So let's call this equation as equation 1 and this as equation 2. So now equation 2 minus equation 1, it will give you IC2 minus IC1 is equals to beta. I am just taking beta common. IB2 minus IB1, right? And I can also further write this as delta times of IC is equals to beta times delta IB. Can I write it or not?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. So my friend, before moving further, I just want to introduce a small resistor at this point. Let's first duplicate it and okay, here we have. Let's first erase this part. So since I was explaining you the cutoff and saturation part, and I didn't mention the resistor at this base side. So now you will have a resistor at this point. and this we call as VI. Okay. Let's call this resistor as RB, and this resistor as RC. Is this clear? See, my intention was not to confuse you earlier. That's why I didn't mention the thing like resistor. See, the potential at this point will be 0.7, even at this point, after this resistor, at any point on the wire. That's why in the earlier part, I didn't mention this resistor. But now we need this resistor because it will help us to, like, it will have some role in the relationship between VI and V. Clear? Okay. So can anyone tell me the relationship between VO, RC, IC, and this 3 volt? Like, what will be the relationship between this part of the circuit? 3 volt, IC, RC, and let's call the potential at this point as V. Or let's call it as V output. V output is more preferable. You have a 3 volt of potential over here. This is your resistor RC. This is your V output, and the current flowing through this is IC. So what will be the relationship between 3 volt, VO, RC, and IC?
The V
Come
naught
on.
is equal to 3 volt minus IC into RC.
V naught equals to
3
3
volt
volt.
minus IC into RC.
See, it will not be like 3 minus IC RC, right? Yes,
sir.
you are correct. Yes. So how, like, 3 volt minus VO delta V equals to delta like potential difference is equals to I into RC, right? So IC into RC. Okay, clear?
Yes, sir.
Similarly, can anyone tell me the relationship between, okay, let's call this current as IC. The relationship between VI, 0.7, RB, and IC. And the concept of 0.7 volt is clear, right? Because it's minimum potential you should have to clear this barrier. That's why I kept 0.7 over here, right?
Sir, that will
So
be
what,
IB, I think.
which, yes, you are right. It will be IB. Thank you. Okay, what will be the relationship between this VI, IB, 0.7, and RB? Let's call this equation as
Vi
equation,
minus 0.7 is equal to
yeah,
I
VI
IBRI.
minus,
R.
yes, 0.7 equals to IB into RB. This is our equation 4. Okay, now repeat the same process which you follow over here. What I mean to say is that, can I write the equation 3 in the delta form? Like, if you apply delta on the third equation part, I mean to say delta on 3 minus VO is equals to delta. I'm just operating it with delta. So delta of constant is always 0. So can I write, see, if this is not clear, I'll explain it again. Since RC is constant, can I write it like this? See, do one thing. Forget about this delta
Yes, sir.
operator part. Just do one thing. Add VO1 over here and IC1 over here. And in the second equation, use the same equation. Instead of 1, use 2 over here. Clear? And if you subtract the both equation, you will get the equation like this. Clear?
Clear, sir.
And
Yes,
we
sir.
will, yeah, and we will also apply the delta operator on the fourth equation. This is our fourth equation. So after applying the delta operator on this fourth beautiful equation, we will get delta of VI is equals to, since delta of constant is 0, is equals to RB into delta IB, correct? Clear till this point?
Yes, sir.
Yes. Now, my friend,
Yes, sir.
just take the ratio of this two equation. Minus delta VU upon delta VI is equals to delta RC upon RB, and delta IC upon delta IB is nothing but a beta,
Beta.
right? Yes. So can I write delta VI is equals to just a minute. I'm just taking the equation. I'm just taking the ratio of this two equation. Okay, upon delta VI is equal to RC upon RB into beta. Okay. Now do one thing. Let's represent the whole equation in the form of like simplified version. Minus of delta VI into RC upon RB into beta. And my friend, please note this equation in your book or whatever copy you have. This is very important equation. Okay, we have just, okay, let's not make it dirty. So we have derived the equation between VO and VI. Like how, and don't worry, I'll also explain the like everything, like what is minus sign doing over here and this whole equation part. But till this point, is the derivation clear to all?
Yes, sir. Clear.
Yes. Yeah.
Yes, sir. Please.
So what we have, my friend, we have delta VO is equals to minus of, I'm just shuffling the variables on one side into beta into delta VI. And my friend, if you recall, we call this term as voltage gain. See, this equation is of current gain. This beta is current gain, this beta constant. And since your RC is constant in the circuit, RB is constant, and beta we have already fixed it 200. This whole term will be constant, right? And we call this term as voltage gain. Uh, Obviously, this part will be like negative part will not be there. Voltage gain is always a positive quantity, but you get it right. Okay. Now, my friend, I'll explain you what this minus sign. What does this minus sign is telling you? So before explaining it, you all know that if we increase if you increase the potential, like if you increase the VI over here, what will happen to VO? Can someone tell me what will happen if you increase the VI or if you increase the potential at this VI part? Just now we have saw that, right? If you increase the potential at this point, the current flowing through this will also like it will get like reduced, right? See, let's say you are using like value over here like point, let's say 1. So 1 minus 0.7 is 0.3, and let's say if you are using 2 over here, so 2 minus 0.7, so obviously you will have more potential difference. Okay, so okay, let's not create a confusion over here. Let's draw a graph first. We need a two graph. Let's say here you have VI versus T, and here you will have VO versus T. So let's say you have a graph like this. So can anyone tell me what will be the graph of VO versus T will look like by just observing this equation? if I'll explain you. If the difference is negative, then negative into negative will be positive. So delta V will equal to positive value, some positive value. So in the first half, your delta Vi is positive, right? Since your Vi is increasing with time. True? Got it? Because if delta Vi is positive, positive into negative is negative, and delta Vo equals to negative. So our Vo versus time will look like this for the first half. True? Clear? Is this clear? Come on, guys. I
Sir,
need
explain in,
interaction.
sir, explain again, please.
Okay. I'll explain it again. No worry. So this derivation part is clear to you, right? Like how I derive this relationship between input and output voltage, output and input voltage, right?
Yes, sir.
So imagine if your delta Vi it's positive. Let's say for a time being, let's this delta Vi be a positive value. So what will be this whole value will be equals to, whether it will be positive or negative. If this is your positive, then whole value will be negative or positive.
Negative.
Negative, right?
Negative.
So yeah, so that's why your delta V naught will be negative. It means your change in the voltage should be negative. And if you look carefully in the first half, your Vi is increasing with time. So I can say over here, like delta Vi in the first quadrant, it's greater than zero, right? Because it's increasing with time. So that's why our Vo versus time should decrease. Clear? Clear?
Yes, sir. Clear.
Yes.
Yeah. Now delta Vi, since you are now the derivative of the function, the derivative is decreasing. The slope is decreasing, right? So delta Vi now it's less than zero.
It's
So
positive.
yeah, it will be positive. So you can see, right, how the change in the potential is changing the potential, it's changing the output voltage, right? So that's why, like in the first case, when you were increasing the current IB, see how you can increase the IB current by increasing the input voltage. And since your potential, like VB was also, or V input was also increasing, that's why your output potential was decreasing. You got this point now? See, I have explained it through the first point also, and I have also explained it using the graph or using the equation. Clear?
Yes, sir.
Yes. So this is all you have for the transistor, and we have successfully discussed like how you can use a transistor as an amplifier. But we should also look the other use of the transistor, which is as a switch. Okay, so this discussion will be very small, like how you can make it behave like a switch. So let's draw like our old sketch over here. Uh, I'm representing the transistor with the with this thing right now. So this is your IP, this is your IC, and my friend, let's connect a bulb across this part. And this, let's say this is as 3 volt. This is at some output voltage. Here you have 0.7, and here like this is your connected to the ground. So my friend, Okay, we have this. There is a small mistake in this diagram. Your output potential will be at this green point because you have used your potential across this, right? RB, RC. Okay. So my friend, tell me if the value of IB, let's say if this is 30 microampere, then what will happen? What will happen if your IB is 30 microampere? What will be the potential at this green point? Just look at the table. It will be zero, right?
0.
Yeah. So if you are having a zero potential at this point, will this bulb glow? No,
No, sir.
right? Yeah. So there will be no, we can say bulb will be in the off state. Can I represent it like this? Bulb equals to zero. It means it is zero. And let's say if your IB, if it is less than, if it is less than uh, 30 microampere, then there will be some potential at this VO, right? You will still have some potential at this point, and your bulb will move to the on state. Okay. So can I say if current through the base, if it's greater than or equals to 30 microampere, your bulb is off, and if it's less than 30 microampere, it's on. So it's working like a switch, right? At 30 microampere. This 30 microampere is not a fixed value. All right, my friend. We are just using because we have taken some value so that it will match the mathematics. But for the explaining purpose, we can say it's working as a switch to the near point of 30 microampere. Clear? See, because at if your potential if the current through the base, if it is less than 30 microampere, then you will have some potential at dot point, right? At green point. And whenever there is a difference between the potential at green point and ground point, which is zero voltage, your bulb will glow, right? So this is in this way you have built a you have successfully built a switch, and this 30 microampere is very small. You can manipulate this value. Like it's very easy to manipulate this value. You don't need any moving part over here. You just need to control the current through the base, and you can turn it on, off, or on according to your. So this is a working of transistor as a switch. Any doubt in the amplifier part and in the switch part? See, guys, we nearly like we have used 2 lectures for this transistor part just to explain this all this stuff, like to how it's working like an amplifier and how it's working like a switch and so on. See, this I agree. This might be confusing, like because we have used a lot of slides over here. But but if you watch this lecture again, if you see the recording of this again in the after this lecture, you will see it's nothing hard. Like there is there's not even a single complicated thing I have used over here, right? It's all mathematics. Okay, and this was all the story about the transistor. Okay, any doubt till this point?
No, sir.
No, sir, no
Yes,
doubt.
yeah. Someone say, sir.
Sir, we can use transistor as amplifier in only IB less than 30 microampere, sir.
Yes.
And for switch,
For what making it behave like a switch, you
yeah, yeah.
use a value near the 30 microampere. If it's greater than 30 microampere, voltage at point green is 0. That's why your bulb will not glow. And if it's even less than 30 microampere, there will be a small glow in the bulb. And if you even make it less, like at 10 microampere, you have more potential at this point. So
As voltage increases.
yes, voltage at this green point. Okay. So this was all about the transistor. And okay, let's finish this part also. The concept of Czochralski method. And okay. So guys, like before discussing this method, can anyone tell me like what is the process of making silicon chips? Like how we use or how we like what are the raw ingredients which we use to manufacture a semiconductor chip? Any idea? Come on. First, let's check how many people. Oh, we have only 20. No worry. So if you recall from the first session, you know that around 25 to 29% of Earth crust is made from silicon or oxides of the silicon, right? So the silicon, which is so the sand which is rich in silicon, we call it as quartz sand. Okay? So there are some famous.
Hello.
Yes.
Till what time will this class be continue?
Like more 10 or 15 minutes.
Because I need to leave right now. So can you ensure that if a recording will be posted today?
Yes. It will get posted by today. I'll make sure of it. Don't
Yeah,
worry.
please. Because I need
Yes.
to leave because of some.
No worry.
Yeah,
Since you have
thank you.
attended the important part, it's all right
Mhm.
if you leave.
Okay,
Okay.
thank you.
Yeah, no problem. So my friend, there are some important co location in our India. Like I think it's one of them are near Srinagar. So that's why it's like since it's very the land at that part, it's very rich in silicon and dioxide. We like there are some dispute at that part, but India it's like it has self sufficient land to fulfill the requirement of this silicon. It's a different story that every year we face a shortage of silicon chips, but honestly, we have lot of potential in our land. It's all like it's we just like we are just staying behind in the terms of the technology and the infrastructure, and also some like geopolitical disputes and all this stuff. Okay? So, but it's not a matter of concern for us in this lecture. So, uh, the type of soil which is rich in silicon, we call that quartz sand. Okay, and when you collect this quartz sand, what you do, let's say quartz sand it has a majority of silicon dioxide. So what you do, you pass this through the crusher and like uh, mining and crushing of this silicon dioxide is there, and you get a small chunks like small dioxide like a small like a sand. Okay, so what you do, you react this silicon dioxide with carbon in a electric furnace. Okay, we also call it as electric arc, and you get a silicon plus carbon monoxide. So let's balance this equation first. 2 on the left side, 2 oxygen I will need on the right hand side. Okay, so I have 2 carbon over here, so 2. Okay, so this equation is balanced. So this process is done in the electric arc, okay, at around 1800 to 200 degrees Celsius. Okay, This is the first process. Okay. And after this, you get a silicon which is 98 to 99% pure. You might say, okay, we have quite good purity of silicon. Why don't we use this directly in the manufacturing of semiconductor? But my friend, you need a very, very, very high quality of silicon, because even you have 1% of impurity. And I already explained the transistor which are used in the modern equipment like your laptop or smartphones. It's very small. It's in the range of 100 nanometer. So even an impurity of 1% will will make the transistor as useless. It will not conduct the electricity. There will be many defects. Okay. So this is our first process. You collect a good quality of sand having a rich silicon dioxide. You pass it in the furnace. This is a kind of furnace, and you basically you add a carbon. Carbon means like coke and uh, charcoal and graphite. All this stuff you add, and you pass, basically you heat this whole equipment using electric arc, or sometimes mostly it's heated using electric arc. And then you form silicon and also carbon monoxide. Since this gas is dangerous, further this gas is oxidized, but it's not our concern. So this is first reduction process. Why reduction? Because your oxygen is getting pulled out from the silicon. It's a reduction of the silicon. You know the concept of a basic concept of reduction or addition, right? Oxidation, right? Reduction means the loss of oxygen. So silicon is getting reduced over here, and carbon it's getting oxidized. Okay. Now we have our second process. Since you have got silicon from this part, but it's still not pure. All right. So what you do in the second part, you uh, you pass this silicon in the HCl gas. Okay. And in this process, you get a gas which we call it as trichlorosilane, and you get a hydrogen molecule over here. So first, let's balance this equation. We have 1, 2, 3 hydrogen on this side, so we need
3 at
3.
HCl.
Yeah. So it will get balanced. Good. Gas, gas, and this is just in the solid form. So you pass this silicon in the HCl gas, okay, and you get a product trichlorosilane, and this is gas. No, it's like you will say it should be in solid, but no, this is in the gas. Trichloro. Okay. Okay. And my friend, this process is known as Simon's process. Okay. So this process is known as Simon process. Okay. You get a silicon gas, and actually it's a process like you have a silicon rod, and on that rod you pass a HCl gas perpendicular to the rod, and then you get a gas. But we are just looking on the equation side. And then since you have this part, what you do further, you react this thing with the H2 gas. So you have SiHCl3. You react this gas with the hydrogen gas to get silicon and HCl gas again. Okay. So first let's balance this 3, 3, 2, 3. Oh, I just need 3 over here. Here, I think it's balanced. Yeah. I guess I have made a mistake. This is not this is not a Simon process. Actually, this is a Simon process. This part. So this is the Simon process. Sorry for the inconvenience, guys. This is the Simon process. To get a solid silicon back from the gaseous silicon part using the hydrogen gas. And this silicon, guys, this is like, it's very pure silicon. Like it's around 99.99, something like this, of the purity. But my friend, even till this point, we do not stop and we go further. Why? Because now the silicon which you have got from this part, it's a polycrystalline silicon. Now, my friends, what is polycrystalline? Wait, I'll explain you. Let's say this is your crystal of silicon. Now, polycrystalline means it's made from silicon, pure silicon, but it's in the like part of crystals which have came together. That's why we call it as polycrystalline. So in each crystal, you have a proper silicon bonding, like this. It's very proper. But since you have a polycrystalline, there are many defects in the structure of silicon. So that's why we need a Czochralski method to form this, to convert this polycrystalline silicon to the monocrystalline silicon. And monocrystalline silicon will be, it will look like this. You have clear, have one crystal and it will not have any defect. Got it? This is polycrystalline and also poly CRY, and this is monocrystalline. Okay, got it? So
Yes,
to
sir.
convert the polycrystalline silicon to the monocrystalline, we use process known as Czochralski method. Now, in the Czochralski method, what you do first, you have a, let's forget this image. Let's have a container over here. What you do, you first put like polycrystalline over here, and what you do, you heat this part, and the boiling point, or the sorry, the melting point of silicon, it's around 14 degrees Celsius. All right. So if you give heat, it will start to melt. And once this all polycrystalline, once it's in melt form, what you do, you put a small pure crystal, pure silicon. This is a pure silicon rod, monocrystalline silicon rod. You put this small rod inside this liquid. So let's imagine this is our pure rod. You dip a pure rod inside this melted form of polycrystalline silicon. This is pure rod, right? And you start to rotate this pure rod around its axis. Okay. Now, due to this, there will be a deposition of silicon on this rod, and generally we call this rod as a seed. Seed, from seed you get plant, right? So in the same process, we also want to behave in the same way. From the seed, you want to generate a whole monocrystalline silicon. So you start to rotate this rod like this, and the silicon from the polycrystalline state, it will start to deposit over the seed. Okay, and you keep rotating this rod till you manage to extract every piece of silicon from this melted form. So we also have some data, like there is pull rate also. So what you do two process simultaneously. You rotate this rod of seed and you also pull it upward. So because of this, there is a deposition of silicon on this rod, and we call this as ingot. Okay. So I have also mentioned over here, this is called as silicon ingot, obtained from the Czochralski method. So you can see this whole part, it has been extracted from this, from very tiny rod. You can also imagine it like a in the it's similar process to the making of the cotton candy, like sugar candy, like which is in the pink color, like some people still used to sell it on the, like, on road. So it's similar process to this Czochralski. You place a small stick inside this sugar solution. You keep it rotating, and the solution of sugar will start to deposit on the stick. Okay, so it's similar, and in this way you obtain this silicon ingot, which is 99.7 times 9%. It's
Sir,
such a pure. Yes, yes.
sir, is there any chemical reaction for this
No, there is
Chokrasky
no,
method?
no, there is no chemical reaction. Since you are using a pure silicon in the melt form, you just need to convert this state into this state, okay? To polycrystalline to the monocrystalline. See, the silicon which you obtain from here, it's also very pure,
Yes, sir.
99.9999, similar to your original silicon. But since its structure, it has a defect in its structure, and we want our structure as a clean and neat, constant throughout the crystal. So that's why we use this method to have a proper structure of silicon. Okay. So this was all about the Czochralski process. And once you obtain this pure silicon ingot, what you do using there is one process known as a diamond saw cutting. So using a wire made from, it has a diamond in it. So you cut this part into like a thin plates like this, and so on. So now this further plate will be used in the manufacture of silicon. So generally the length of this part, it's around 1 to 2 meter. All right. And the diameter of this silicon ingot is in between 100 micro millimeter to 400 millimeter. Okay. And now you cut this into small part, and now this is sent further for the manufacturing of like manufacturing of chips and so on. Okay, so this was all about the Czochralski process. Any doubt?
No, sir.
So can you give a short summary of this process again? Like a short summary.
Okay, of this Czochralski, right?
Yes, sir.
Yeah. So what you do at first, you have a polycrystalline surface of the silicon. Since it's in the polycrystalline form, what we want a single crystal which is uniform across the crystal. So you take a melted form of polycrystalline and heat it over a temperature of 40 degrees Celsius. Okay, and you insert a small silicon rod which is very pure. Okay, and what you do, you start to spin that silicon rod, and because of this, the silicon in the polycrystalline form will start to deposit on the rod. And you also pull this rod, like you do two process simultaneously, one
So
spinning
that
and
rod is made
another.
up of silicon.
Yes, it's pure silicon. This rod is pure silicon.
Okay, sir.
This is also, yeah, see, this part is also your pure form, but this rod, it's monocrystalline. If you look inside the structure of the atom of this silicon, you will see it's very linear and constant. It will have very few amounts of defects. And as you pull this upward, you get a thick rod like this, and we call this as silicon ingot. And this is 9n pure. 9n pure means you add a decimal at the second place, and you get 99.9999% purity of this. Okay. And basically the need of this process is to convert the polycrystalline to monocrystalline. Okay, we are just changing the structures of the atom of silicon, and then it's cut into small parts, and then your transistor and all these things are integrated on this silicon plate. Okay, clear?
Yes, I got it.
Yeah. Any doubt?
No, sir.